Okay, good morning. Let me start now. Uh, Today I'll prove some results about spectrum of a compact operator. Uh, Let me state the theorem first. Let V be an infinite dimensional Banach space and let T be a compact operator. Compact operator on V. Then we have that 0 is always in the spectrum. This is easy to see. Second part is every non-zero lambda in spectrum of T is an eigenvalue of T with finite geometric multiplicity. So for an eigenvalue, geometric multiplicity is the dimension of the eigenspace corresponding to that eigenvalue. Right? So here we are saying that if lambda is any non-zero point in the spectrum, then it has to be an eigenvalue and the dimension of the eigenspace has to be finite dimensional. Next part says that if we have any sequence, if lambda n is a sequence of distinct non-zero eigenvalues of T, and if lambda n converges to 0, then if lambda n converges to some lambda, then lambda has to be 0. So in particular, this says that the non-zero eigenvalues in fact non-zero or any point in the spectrum we know is an eigenvalue. So I can say that non-zero elements of the spectrum are all isolated. So if lambda is a non-zero point in the spectrum, then it has to be an isolated point. Right? So there cannot be a sequence of lambda n in the spectrum which converges to any non-zero lambda in the spectrum. And D part says that one of the following alternatives hold. So first one is that the spectrum of T may consist of only 0 or spectrum of T minus singleton 0. This can be a finite set, or spectrum of T minus 0. This consists of a sequence of eigenvalues which converges to 0. Right. So it is of course possible that a spectrum has only 0 in there, because if you take the 0 operator, then we know that the only point in the spectrum for that will be just 0. So spectrum can consist of only 0 element, and it is possible that a spectrum of T consists of only finitely many elements. So in that case, this spectrum of T minus 0, this will be finite set, or spectrum can be countable. So what this says that the spectrum of T cannot be an uncountable set. So it has to be at most countable set. And if you exclude the 0 element from the spectrum, then all the lambda in the spectrum of T, excluding 0, they have to be eigenvalues. And if they are infinitely many, then the limit of those lambda n has to be equal to 0. So this is the last one. And let's see, this A part, like 0 belongs to the spectrum of T. If this V is finite dimensional, then of course 0 need not be in the spectrum, because in that case we have only eigenvalues. So this is if V is infinite dimensional and T is a compact operator, then we are saying that 0 has to be in the spectrum of T. For finite dimensional, of course, we know that we have only eigenvalues, and then we know that the eigenvalue geometric multiplicity has to be finite. So therefore, this theorem we have stated only for infinite dimensional Banach space. Because for finite dimensional, we know everything. So let us prove A part first. So for A part, we have to show that 0 is not in the spectrum. So when is 0 in the spectrum? What is the meaning of 0 in the spectrum? So since T is a compact operator, on an infinite dimensional Banach space, T is not invertible. Right? Is it clear? If we have a compact operator on infinite dimensional space, then it cannot be invertible. Why is this? because if T is invertible, then we have T is a compact operator, and if T inverse exists, then what can you say about T inverse T? That will also be a compact operator, right? The compact operator, it forms an ideal. So if you multiply by any bounded linear operator, then the product is again a compact operator. But that will say that identity is a compact operator. But on infinite dimensional space, identity cannot be a compact operator because the unit ball in infinite dimensional Banach space is not compact. So this is because if T inverse exists, then identity equal to T inverse. This is compact, which is not true, as this space is infinite dimensional. But T not invertible means that 0 is not in the spectrum. So if I write lambda I minus T, right? So 0 I minus T, this is not invertible. Which implies 0 belongs to a spectrum of T. So first one is clear because a compact operator on infinite dimensional space cannot be invertible. Therefore, 0 has to be in the spectrum. For the second one, we have to show that every non-zero element in the spectrum is an eigenvalue, and the dimension of the eigenspace is finite. So for that, okay, so let us prove B part. So let lambda be not equal to 0. and lambda belongs to a spectrum of T, then we want to show that lambda is an eigenvalue first of all. So for that we have to show that lambda is an eigenvalue of T. So this means that that is lambda I minus T, the kernel of lambda I minus T, this has to be non-zero. So let's write this lambda I minus T as lambda times identity minus 1 by lambda times T. Because lambda is non-zero, I can write like this. So now we will use one result. So maybe let me write it separately. So let me write it on the next page. Lemma. Let T V to V be a compact operator on a Banach space V. Then the kernel of I minus T, this is finite dimensional. And second one we will show that the kernel of I minus T is 0 if and only if the range of I minus T is V. So B part says that I minus T is 1 if and only if I minus T is onto. Right. So this is understood as like if you have a finite dimensional vector space and then if you have any linear operator, then we know that a linear operator is 1 if and only if it is onto. So that just follows from the rank nullity theorem. So here we are saying that same result is true for identity minus T is 1 if and only if identity minus T is onto, provided T is a compact operator. So this identity minus T, this is called a compact perturbation of identity operator. Right? Identity operator, we know if like V is a infinite dimensional, then that will not be compact. So, but if we perturb the identity operator by a compact operator, then this is saying that identity minus T is 1 if and only if identity minus T is onto. And the first part is saying that the null space of this identity minus T, it has to be finite dimensional. So that means that if we have 1 as an eigenvalue, then its geometric multiplicity has to be finite. So So let us first prove this lemma. So let x is equal to the kernel of identity minus t, and b1 be the closed unit ball in x. So this kernel of any bounded linear operator is always closed. So this x is a Banach space, and we are taking the closed unit ball in this x. So if x belongs to this closed unit ball in kernel of I minus t, then norm of x is less than equal to 1, and because x is in the kernel of I minus t, this x is equal to t of x, right? Because the I minus t of x is equal to 0, so that will say x is equal to t of x. So if x is in the unit ball in this space x, then x is equal to t of x, and norm of x is less than equal to 1. So therefore this b1 is contained in t of b, where b is the closed unit ball in v. Now since t is compact, this means that t of b will be compact. So t of b closure is compact, and hence b1 is compact, right? Because b1 is a closed subset of this t of b a closure compact set. So b1 will be a compact set. So the closed unit ball in this x, this is the compact, and therefore the therefore it has to be finite dimensional. So, so hence this x is finite dimensional. Right? Because the closed unit ball of an infinite dimensional Banach space is not compact. So this is again we are using that same result, since closed unit ball in infinite dimensional Banach space is not compact. Right, so this proves the A part, that kernel of I minus t is finite dimensional. Now for B part, we want to show that kernel of I minus t is 0 if and only if range of I minus t is V. So let's assume that kernel of I minus t is 0. Then we have to prove that range of I minus t is V. So suppose it is not. Suppose V1 equal to range of I minus t is not equal to V, then V1 is a closed subspace of V so this also maybe I should have written so let us see. So okay, I'll write this maybe right now. I'm not proving this. So for any compact operator T, range of I minus T, because in general range of bounded linear operator need not be closed, but for compact operator again this range of I minus T is closed, and also this range of I minus T is the orthogonal complement of kernel of I minus T star. So this right now I'm not proving, so you can try to prove this or we can do it later. So we will use this fact that this range of I minus T is closed subspace. So therefore it is also a Banach space. Also, if we take any x in V, then T of x minus Tx, this is equal to identity minus T of Tx. So this shows that this belongs to the range of I minus T. So this implies T of V1 is contained in V1, right? Because V1 is range of I minus t. So if we take anything in the range of I minus t, this is in range of I minus t. So we are saying that if we take any element in range of I minus t, then t of that is also in range of I minus t. So t of V1 belongs to t of V1 is a subset of V1. So if we restrict t to V1, we get this. So therefore, t restricted to V1, this is from V1 to V1 is this is also a compact operator because t was compact. So this is a compact operator, and therefore if we look at I minus t, this restricted to V1, this also has a closed range. Again, we are using that same result that if we have a compact operator, then range of I minus t is closed. So now we will do this same thing again. So if we take V2 equal to I minus t of V1, so claim is this V2 is a proper subspace of V1. So suppose not, so suppose V2 is equal to V1. If V2 is equal to V1, then for any x in V, there exists y in V such that identity minus t of x is equal to I minus t square of y. Because V1 was the range of I minus t and V2 is range of uh, I minus t restricted to V1. V2 is I minus t V1. So if V2 is equal to V1, then for anything in the range of I minus t, that is I minus t of x, this has to be in the range of I minus t of V1. So that means that uh, it has to be equal to I minus t of I minus t of some y. So we can write like this. So this implies x is equal to I minus t of y. This is because I minus t is 1, 1. So we are assuming that kernel of I minus t is equal to 0. So therefore, this will imply that uh, x is equal to I minus t y. But this is saying that any x can be written as I minus t. So this implies v1 is equal to v, which is we assume that this V1 is not equal to V. So this gives a contradiction. Contradicts our assumption. So if we had assumed that V1 is a proper subspace of V, then this V2 will again be a proper subspace of V1. So now we can repeat this same process. So, so inductively, we get a decreasing sequence of closed subspaces of V. Let's call this as Vn. Such that Vn is equal to I minus T raised to N of V. Or V1 was range of I minus T. V1 is I minus TV. V2 is I minus T of V1. So that is I minus T square of V. So Vn will be equal to I minus T to the N of V. And Vn plus 1 is a proper subspace of Vn for all n. So now we will use Ree's lemma. So by the Ree's lemma, there exists Un belonging to Vn such that Un is a unit vector and distance between Un and Vn plus 1 is bigger than equal to half. Ree's lemma said that for any epsilon, I can find this Un such that distance between Un and Vn plus 1 is bigger than equal to epsilon. So we get this. Now let's look at what is T of minus Un. So this can be written as Un minus Tun minus minus Tum plus minus Un. So what can we say about Un minus Tun? This belongs to range of uh, I minus Tun, and Un is in Vn. So this is an element of Vn plus 1. Right? Un minus Tun, this belongs to Vn plus 1. And similarly, this minus Tum, this is in Vm plus 1. So if we say n is bigger than m, then this Vn plus 1 is contained in Vn, which is a subset of Vm plus 1, because in this case n is bigger than equal to m plus 1. So Vn is a subset of Vm plus 1, and Vm plus 1 is contained in Vm. So therefore this here um belongs to Vm and un belongs to Vn. So this difference will be in, so therefore, yeah, so this uh, here un, this is in Vn, and which is contained inside Vm plus 1. So what we get is T of minus un is equal to minus w for some w belonging to Vm plus 1. Right? So we have here, and then everything else is in Vn plus 1, right? Because this Vm plus 1, Vn plus 1, this is a subset of Vm plus 1. So this is in Vm plus 1, this is in Vm plus 1, and un is in Vn, which is also in Vm plus 1. So this whole thing is minus a vector in Vm plus 1. So therefore, this will imply that this norm of minus Tun, this will be bigger than equal to half, because we know that the distance between and Vm plus 1, that is bigger than equal to half. So here we have, well, this vector is in Vm and this is in Vm plus 1. So this has to be maybe let me write, this is bigger than equal to distance of um and Vm plus 1, which is bigger than equal to half. But this will imply that Tun cannot have a convergent subsequence. But this will contradict that T is compact, because T is compact and un is a bounded sequence. So TUN must have a convergent subsequence. But this says that TUN cannot have a convergent subsequence. So we get a contradiction. So therefore our initial assumption was wrong. So hence this range of I minus T, this has to be equal to V. So this was to show that if I minus T is 1 1, then I minus T is also on 2. And for the converse, if we assume range of I minus T is equal to V, then the kernel of I minus T star, this is equal to the orthogonal complement of range of I minus T, and range of I minus T is equal to V. So this is V perp, which is equal to 0. But T is compact, so T star is also compact. T star is also compact. This will imply that this kernel of I minus T star equal to 0. This implies range of I minus T star is equal to V star. This also has to be onto, and then we get kernel of I minus T, which is range of I minus T star per, which is equal to 0 again. Okay, now let's come back to, I should have proved this result before. So now we have this proof of B part of the theorem. So what we said is that lambda belongs to the spectrum of T, and lambda is non-zero. Then lambda I minus T we write as I lambda times I minus lambda inverse T, and now since T is compact operator, right? So now let's say, so now by the lemma, this I minus lambda inverse T, this is 1 if and only if I minus lambda inverse T is onto. So if this we assume that the uh, kernel of lambda I minus T, this is same as kernel of I minus lambda inverse T. So if we have that this lambda is not an eigenvalue, then this will be 0. So if lambda is not an eigenvalue, of T, This will imply kernel of I minus lambda inverse t. This is 0. And this implies this range of I minus t inverse, I minus lambda inverse t. This has to be V. So that means that this I minus lambda inverse t is invertible. So this will imply that I minus lambda inverse t is invertible, which implies that this lambda I minus t, this is same as lambda times I minus lambda inverse t. This will also be invertible, but this implies lambda is not in the spectrum of t. So therefore, if lambda is in the spectrum of t and lambda is non-zero, then it has to be an eigenvalue. So this proves that any non-zero element in the spectrum is an eigenvalue, and then again why this eigenspace is finite dimensional. So this, so this is again by the lemma. Part A of the lemma says that if we have any compact operator, then kernel of I minus t is finite dimensional. So using that, is kernel of lambda I minus t, this is equal to kernel of I minus lambda inverse t. This is finite dimensional by part A of the lemma. Right, so we have proved this part B of the theorem, which says that any non-zero element of the spectrum has to be an eigenvalue of t and it has finite geometric multiplicity. Let me stop here. So in the next class, we will prove part C and D of this theorem. Yeah, so as announced before, tomorrow we will have a quiz. So tomorrow at 11 o'clock, you should join. I'll send the link for the quiz separately, because there will be like different link for different students. So you will join using that link for the quiz, and then it will be on grade scope. So you will get the question paper and around 30 minutes to do the quiz, and then you will upload your response there. So tomorrow we will not have any lecture class. We'll have the quiz tomorrow, and then we'll have the next lecture class later.